Okay, so to pick up where we left off in the demo, I want to sketch a graph of C of x by plotting all the points that we just figured out. So -4, 0, -3, about 7 1/4, -2, 8.65, -1, 6.15, 0, 1.45, 1, 3 1/4, -3 1/4, 2, -5 3/4, 3, -4.35, and 4, 2.9. Okay, so if we connect those with a nice smooth curve, we get something like that. Hey, that looks very similar to, oops, missed a section there. That looks very similar to the antiderivative we sketched at the very beginning of the lesson. Right, this one that we did without the help of any numbers. We were just sketching the antiderivative based on the sign of the derivative and the increasing, decreasing behavior of the derivative. But it looks very much like this sketch that I just drew of the cumulative area function. Okay, let's define C of x differently, a different cumulative area function. This time I'm going to integrate starting at 1. So C of x is going to be the integral from 1 to x of f of t dt. So in the original that we just worked on, it was -4. The C of x was defined as the integral from -4 to x of f of t dt. So I already gave you all the values, the cumulative area values, but just to verify, to make sure we know what we're doing here, I want to verify 2 of these. So C of 1, I want to make sure that that comes out to be 0. Okay, so C of 1, the way we've defined this is the integral from 1 to 1 of f of t dt. So it doesn't matter what graph I'm looking at, but it's f of t, which is this original graph. But the area between 1 and 1 is going to be 0. Whenever the bounds are the same, the integral is 0. So that checks out. And then I want to evaluate C of -2. So my definition for C of x is the integral from 1 to x, so -2 in this case, of f of t dt. So this looks a little weird because the lower bound is typically on the bottom. The smaller bound is the one on the bottom. So if I change the order of the bounds to be -2 to 1, I have to put a negative in front of the integral. All right, so this says find the area under f of t dt from -2 to 1. And then make it negative. So this equals negative whatever I calculate as the area under f of t from -2 and 1. So I go back to f of t, my original graph, little f, and I need to calculate the area between -1 and 2. So here's -1, here's 2, so I need this area. And so I can get that area by adding up the areas I've already labeled. 4.7 plus 4.7 plus 2.5 is 11.9. But it's under the x-axis, so it's negative. So I'm going to have -11.9 is the value of that integral. So I go back over here and I put -11.9, but now there's also this other negative here. So -11.9 is 11.9. Okay, and that verifies this value. We have 12, but these are estimates because the scale was not fine enough to get a really good value. Okay, so how does the graph in number 2, on the graph, plot the 2 points that correspond to C of 1 and C of -2. So C of 1 is 0, and C of -2 is 11.9. So those 2 points are on the graph. If I plot the rest of those points, I get this looks like a cubic polynomial graph. Okay, so how does it compare to the graph I drew in number 1? So I'm just going to scroll up a little bit so I can see them both at the same time. They have the same shape, but it used to be that f of -4 was 0, and now f of -4 looks like it's approximately 3. And let's see, f of 1, say, used to be about -3, and now f of 1 is 0. So these have the same shape, but this second one is vertically shifted up 3 units from the original. So this is a vertical shift up 3 units. Okay, so both of my graphs that I just drew of cumulative area functions look similar to the antiderivative I drew right at the beginning of the lesson. The first one was identical. The second one has the same shape, but it's a shift. And we happen to know that antiderivatives, and any 2 antiderivatives of a function differ by a constant. There's always that plus c. So it's starting to look more and more like this cumulative area function is an antiderivative of little f. So the function graphed on the left in problem 1, the original function, little f, is t squared minus 5. So I want to find a formula for its antiderivative, capital F, given that f of -4 is 0. Okay, so capital F of t, an antiderivative of t squared would be 1/3 t cubed. An antiderivative of -5 is -5t plus c. And then to figure out the c, I can use this initial condition that they gave me. So f of -4 would be 1/3 times -64 plus 20 plus c equals 0. When I solve for c, I get 4/3. So my function f of t, the antiderivative of little f of t that goes through the point -4, 0 is 1/3 t cubed minus 5t plus 4/3. So how does this function compare with the one I graphed in number 1 with c of x? So let's see, if I start plugging some values in to this function f, well, f of 0, well, let's do f of -4, we know is 0, and that was true on my original function. And my c of x function, f of -4 was 0. Let's see what happens if I plug in 0. Do I get approximately 1.45 in this formula? F of 0 is 4/3, which is 1.33. That's pretty close. Pretty close. Remember, our original numbers are estimates. Let's try f of 1. I should get -3 1/4 or something pretty close to that. So I'm going to get 1/3 minus 5 plus 4/3. So that's 5/3 minus 15/3 is -10/3, which is -3.33. That is pretty close to -3 1/4, our estimate of -3 1/4. So I think that the formula that we just came up with is the exact same function as the graph of c of x from number 1, and it's a vertical shift of the graph in number 2. So capital F is the same as number 1 and a vertical shift of number 2. So now we tie this all together. We were originally given the graph of a function. We then sketched a graph of an antiderivative function by only thinking about increasing, decreasing, and concavity. And then we created a table and graph of an area accumulation function. And we discovered that the graph of the antiderivative function, which we just came up with using as a formula, was the same as the graph of the area accumulation function. So it turns out the area accumulation function is an antiderivative of the original function. The area accumulation function, the integral from a constant, any number a, to x, where we accumulate area from a to some value x, that is an antiderivative of the original function. That is called the fundamental theorem of calculus part 2. And when we write it in symbols, it says that the integral from a to x of f of t dt, that is an antiderivative of little f, right? That is an antiderivative, capital F, of little f of t dt. So note that t is a dummy variable, x is the actual variable in this equation. X is the thing that we're plugging in and that changes and we get different outputs for. The value of a is, in some sense, the starting point of the accumulation function. The value of f of a is always going to be 0 because it's the integral from a to a of f of t dt, which will always give you 0. Okay, suppose we want to find an antiderivative of little f of t, which is the square root of 1 plus t squared. Can you do this using a table of antiderivative formulas? No, there is no formula that looks just like that. There's no formula for an antiderivative of radical 1 plus t squared. So instead, we're going to use fundamental theorem of calculus part 2 to construct an antiderivative. So we're all going to pick the same a value. We'll just use 2. So my antiderivative would be the integral from 2 to x of f of t, which is the square root of 1 plus t squared dt. So to find f of 1 and f of 5, I just replace the x in that integral with a 1 and a 5. So f of 1 is the integral from 2 to 1 of the square root of 1 plus t squared dt. Okay, to have our calculator evaluate this, you go into the math menu, choose option 9, which is function integration, fnint, and we type in the bounds, which are 2 and 1. Our function to integrate is 1 plus t squared dt, the square root of 1 plus, typically we use x, but you can use any letter. So I'm going to use t because the letters matter a lot in the fundamental theorem. 1 plus t squared dt. There we go. And I get about negative 1.8. And then f of 5 will be the integral from 2 to 5 of the square root of 1 plus t squared dt. And that comes out to approximately 10.95. So even though we don't have a way to find a formula for the antiderivative of radical 1 plus t squared, we can use technology to find as many points as we want on the antiderivative function. So we found 2 just now, but you could find any one you want. And you can also use technology to graph an antiderivative, which I've got some screenshots there if you want to play around with doing that, but I won't go through it right now. Okay, so this is still labeled activities, but you can see the these last few problems explained in the demo part 2 for this lesson.